So a very common question in exam papers recently has been the kind of question that asks you to match up equations with graphs. So in this video I'm going to show you how to do this for all the different types of equations. You have linear equations, quadratic equations and exponential ones, and we're going to go through each one and show you how to match them up. Now if you don't know how to recognize a linear equation, well, it looks something like this. You notice it has one or two variables in it, and there's no, say, power of 2 or power of 3. It's that the highest power of the variables is 1. So as long as that's true, it's a linear equation, and that means when you draw out the equation, it appears as a line. That's why it's called linear. So the question is, how can you match up these equations with their respective lines? To do this, you need to know a little bit about the formula y equals mx plus c. If you understand what m stands for and c stands for, then you can work this out. So as you probably know, this is a formula in coordinate geometry that represents the equation of a line. And the m stands for the slope, the c stands for the y-intercept. So if you look at the first equation here, it's exactly in this format. In other words, you have y on its own like you have here, and the number next to x is the slope, so the slope is 2, and the y-intercept is 4. So straight away we can match this up with this line, because we see that this line is going through the y-axis at 4. The y-intercept is 4, in other words. Couldn't be this one because that's going through the y-axis at 0. So you can see this is a very quick method of matching up equations with graphs. You can often use this, and it also works with quadratic equations. We'll show you something about that later. So you're not always going to get a straightforward one like this in the exam. You might see the equation written somewhat differently, perhaps like this one here. This is actually the same equation as this one, but you have a 2 next to the y. So what you can't do is say that the slope is 4 and the y-intercept is 8. You have to first of all make sure that y is on its own. So you're going to take that 2, which is multiplying by y, bring it across here and divide it into these two terms here. So 2 into 4x will give you 2x, 2 into 8 will give you 4. So you will end up with this equation. And once you have this equation in the same form as this, then you can start matching it up with the line, because you know that the y-intercept in this case is 4. Again, here's another example of the kind of equation you might get. And similar to this one, you have to kind of manipulate this equation until you get it in the right form. So what we do first of all is try and get the y on its own. So we bring that 2y across here, become plus 2y. 2y equals 4x plus 8. That would be the same as this. And then you get rid of the 2 like we just explained, and you will end up with this equation. So you have to do a little bit of manipulation to get it in this form, is what I'm trying to say there. So the last equation we're looking at here is y equals 2x. Now you notice here there's no y-intercept. Now what this does not mean is that the line doesn't go through the y-axis. It does, but it goes through the y-axis at 0. So it goes through the origin here. So that's, if you see no number at the end of a linear equation, you can assume that the line is going through the origin. So the next type of equation is called a quadratic equation. And to be able to recognize if you're dealing with a quadratic equation, you simply have to look for the presence of an x squared. If the highest power of x is squared, then this is definitely a quadratic function. Now they usually look like this, right? You have an x squared followed by an x followed by a number. But sometimes you might not have any number. You might just have, say, just x squared or 2x squared. So it doesn't necessarily always follow that you have 3 terms. Just be aware of that. So now there's 2 main types of quadratics. There's ones that appear as kind of a U shape, and then there are others that appear as N shapes. And the way you can match these up is simply by virtue of the sign of the x squared. So if it's a plus x squared, then you're going to have a U shape, which is like a kind of a smiley face, if you want to think of it that way, positive. And then you have a minus. If you have a minus x squared, then you're going to get this kind of N shape, so sad face. Now, please be aware that it's only the sign of the x squared that counts, right? So if you see a minus here, it doesn't necessarily mean that it's going to be an n shape. It's the x squared sign that counts. So if that's minus, it's going to be an n shape. Now let's say you didn't remember this fact and you were trying to match these up. Well, there are always more than one way of doing these things. So another way of figuring it out is by looking at the end term. So this is the same as with linear equations. The end number here, the constant, that's actually where the curve cuts through the y-axis. So you can see for the first one, it's going to cut through the y-axis in the negative region. But the other one is in positive region. So you could match them up simply by looking at the end values here, the y-intercept values. Okay, so here are some random equations that we're going to match up with these graphs here. We have examples of linear equations. The first two are linear. The next three are quadratic, and the last one is called an exponential function. Now I'm going to start with the last one because we haven't really talked about that yet. How can you recognize what an exponential function is? Well, it always looks like this: 2 to the power of x or 3 to the power of x. So the x is actually in the power. That's how you can recognize it, and it's easy to recognize the graph because an exponential function will always look the same. It will always look like this. So the curve keeps getting steeper and steeper and steeper, and it never turns around. So your exponential curves will always look in this kind of a shape. So this is the exponential function. Very easy to do. Now, one thing you need to note about this is that the rule about the number at the end signifying where it cuts through the y-axis does not apply to exponential functions. So you notice there's no number at the end here, so you might think that it has to go through 0, but that doesn't actually apply to exponential functions. Only applies to quadratics and linear functions. So let's have a look at the first two now. These are two examples of linear functions. How do we know that? Because there's no x squared involved. Basically, there's no power greater than 1 on the variables. So I'm going to start off with A. We need to find out basically what this looks like when y is on its own. So we need to take this 2, bring it across here, and divide it into both of these. So once we've done that, we can see that we get minus 6 over 2x minus 4 over 2. Now minus 6 over 2 is of course minus 3. So that tells us that the slope is minus 3, and here the y-intercept is minus 2, because 4 divided by 2 is 2. So straight away we know that the line is going through negative 2. So I'd look for the two linear graphs here. Which one of them is going through a negative on the y-axis? It would be this one. It's going through minus 2 here. So this is definitely belong to this equation. So we're going to do the same thing with the equation B. We're going to move these across the equal to sign. So the minus 4x will become plus 4x, and the minus 3 will become plus 3. So we have y equals 4x plus 3. So this tells us that the line is going through 3 on the y-axis. So that would correspond to this line. Of course, we don't really need to do this because there's only 2 lines here. So a process of elimination tells us that this must be the second linear equation here. So let's move on to the quadratics. Again, I go straight for the y-intercept first. Check that out. In this one, it's minus 3. So that means the curve must be going through the y-axis at minus 3. We have 3 quadratic curves here, but only one of them is going through minus 3, this one. So straight away, I can match this up with equation C. So let's have a look at D. Y equals x squared, and again there's no y-intercept, so we then can assume that it's going through the y-axis at the origin, in other words 0, and that could only be this graph here. That's going through 0. This one is definitely not going through 0. So we can match that one up. That's D. And of course, by a process of elimination, the last equation, E, has to match up with this graph here. Now this last equation is an example of a special type of equation which involves a horizontal and a vertical transformation. So if you're not familiar with horizontal and vertical transformations in functions, I'll be showing you an example of this in the last question that we cover in this video. Now, as I mentioned before, it's sometimes not enough just to look at the y-intercept. For example, these three equations have the same y-intercept. They all have a y-intercept of 4, and the graphs would end up looking like these, right? So how do you tell which one is which? For this, you would have to concentrate then on the slope. So this one has a slope of 4, this one has a slope of 2, this one has no slope, nothing next to x, there's no x. So when you have no slope, you actually have a flat line. So I can match up this straight away. It must be this line here. And also, just for noting, if you have a line going straight down like this, like for example through the number 2 there, the equation of that line would be just x equals 2, because x is equal to 2 all the way along that line. So now let's have a look at the first equation. We notice that it has a slope of 4. Now remember, the slope is equal to the rise over the run. So if we change 4 to 4 over 1, we can kind of figure out that the rise must be 4 and the run must be 1. Now if you're not too sure what the rise over the run is, what you need to do is take 2 points. The best 2 points in this particular example to take would be this point up here and then this point down here. So if we take those 2 points from the line, we can figure out that the run is 1 in length. So the run goes from -1 to 0. So that's 1 in length, and the rise is 4. So that tells us that the green line has a rise of 4 and a run of 1. In other words, the slope is 4 over 1, which is this slope, which corresponds to this equation. So this equation corresponds to the green line, and then of course the red line must be the next equation. But you can work it out. You can say, look, the rise is 4 again, but this time the run is 2. From here to here is 2. So it's going to be 4 over 2, which gives you 2. So the slope would have to be 2 for that red line. So let's have a look at this exam question. It says 3 functions f(x), g(x), and h(x) are defined as follows. So here are the 3 functions. First question is solve f(x) equals to 0. Now, the purpose of this video is not to show you how to do this kind of question, so I'm not going to go through that. I'll explain briefly what you should do. What you need to do is replace the fx with what it's equal to. So fx is equal to 2x squared plus x minus 6. So in other words, you get 2x squared plus x minus 6 equals 0. That's a quadratic equation. You solve that and you get your 2 answers for x. And they will be the roots of the function, and they correspond to where the function cuts across the x-axis. So the roots of this one, for example, would be these 2 points here. So you need to do that for these 3 functions, but we're not really interested in that right now. We're more interested in trying to match up these equations with the graphs below. So the first thing you should note is that they're all quadratic functions because they all have the highest power of x of 2, and they're all positive x squared. So remember what that means. They should all be u-shaped. So straight away we can rule out this one, this graph, and this graph. Now a really quick way of figuring out which graphs they belong to is to look at the y-intercept number at the end. So here is -6. So you're looking for one of the graphs that is going through the negative region of the y-axis. So this one is going through 0, so it's definitely not that. This one is going through a negative region, so I'd say it could be this one. If we look at this one here, it's going through 0, so that's not it. This one is not actually going through a positive value on the y-axis. So it must be this one. So diagram 3 belongs to f of x. And so we can do something similar for the second function. That has a y-intercept of +9. So that means it's going through the y-axis in the positive region. And the only one that does that is this graph here. So diagram 5 belongs to g of x. Now possibly the only difficult one is this one here, because there is no y-intercept. That means it's going through the y-axis at 0. And if you remember, there was 2 graphs that went through 0. This one and this one. So how do we determine which one is which? What we need to do here is actually do this part. We need to find the roots of this function. So we put x squared minus 2x equal to 0. So as I said, this is a quadratic equation. So to solve it, we need to factorize this expression here. Now it doesn't have three terms, so we're not going to do it the conventional way. We're going to have to do another type of factorizing, which is factorizing using highest common factor. So we're going to take out the x, that leaves us with x minus 2 equals 0. And once we have the two factors, these two, this is one factor, this is the other, we put them both equal to 0. So x equals 0 and x minus 2 equals 0. We solve this one to get x equals 2. So we have two answers, x is equal to 0 and x is equal to 2. That means the graph cuts through the x-axis at 0 and 2. So it must be this graph. It couldn't be this one because it would have a negative answer for this part. So it's definitely diagram 2, which belongs to this function hx. Okay, this is our last question in this video. This has to do with transformations in functions, and the question here is to match up these two functions with these two graphs. And I'm going to show you a quick way of figuring out how to do that. But first of all, I'm going to explain a little bit about transformations. So what you really need to remember is what the function fx goes to x squared looks like. And I've drawn it in here kind of roughly. It's a kind of a U-shaped curve that where the minimum point is actually at the origin here. And it kind of straddles the y-axis. So the y-axis is like the center, the axis of symmetry of that curve. Now, you need to remember that, and you also need to remember what are called horizontal and vertical shifts. So I'm going to give you an example first of a horizontal shift, right? So this is an example of a horizontal shift. What's happening here is you're adding 2 onto the x. So you're adding 2 onto this x. And what this causes the graph to do is to shift 2 places in the negative direction. So the opposite sign of plus here, it causes the graph to shift 2 places, this graph here to shift 2 places in the negative direction. So this graph will shift 2 places. So now the minimum point would be here, and the graph would look something like this, right? So that's what's called a horizontal shift. If you had, say, x minus 2 here, then it would cause it to shift 2 places to the right, like that. The other thing you need to be aware of is what's called a vertical shift. So what I mean by that is when you add or subtract a number from the function. So the function here was x squared. So if for example we take away 4 from x squared, we're really taking away 4 from fx, which is y. So we're taking 4 away from the y values on this curve. So each point will go down 4 in the y direction. So the minimum point would actually go down to here, and you'd end up with a graph that looks like something like that. So that's an example of a vertical shift in a negative direction. You can see here it actually corresponds to the sign. So if you're taking away 4, it goes down. If you were adding 4, it would go upwards. So there are the two concepts that you need to be aware of to be able to figure this out. So if we look at the first one here, we see that there's a horizontal shift of plus 2. That means it's going 2 places in the negative direction horizontally. So it's moving 2 to the left, so the minimum point would be here. And then the minus 4 is a vertical shift of in a negative direction, so it's going down minus 4. So it's going to go down minus 4. So you see the minimum point is here. So straight away we can match up this graph with the first function here. You can do the same with the second one. Obviously this is the second one, but you can reason it out in the same manner. So x minus 3 means it's a horizontal shift in the plus direction, plus 3. So it's going to, the minimum point is going to go across 3. So it would look something like this. And then the vertical shift again is minus 4, so it's going to drop down 4, and the minimum point will now be down here. So it's going to look like this, obviously. Now, one other thing that you might find handy to know is sometimes you might be asked in the exam to find out what the equation of the axis of symmetry is for a particular function. And as long as you have the function written in this form, in other words, x plus or minus a number in brackets squared plus or minus a number, then you can quickly find out what the equation of the line is. Now, of course, if you had the graph drawn out like you have here, you can just tell what it is by looking at it, because the axis of symmetry is a line going right down the middle, so true minus 2 in this case. So the equation of that would be x equals minus 2, because all along the line x is equal to minus 2. But let's just say you didn't have the graph, you just had this function. You can actually tell from the function itself what the equation is going to be by making this number here negative. So it's a plus 2, so we make it to minus 2, and then the equation would be x equals minus 2. Likewise here, we make the minus 3 negative, so that'd be plus 3. So x equals 3 will be the equation of this one, and you can confirm that by just looking at this. The line is going right through 3 on the x-axis, so x equals 3 is the axis of symmetry. If you like these videos, please consider subscribing to my channel. I hope to upload more videos before the exam this week, and we'll definitely be doing videos on the Leaving Cert next year. So subscribe and make sure not to miss out on those videos. Thank you.